Hello everyone, this is Chemistry Lesson 1, Introduction, Matter and Measurement. First, I'm going to give you a chapter overview. I'm going to talk about the study of chemistry, what chemistry is about, and why it's useful to learn chemistry. Then we're going to look at some fundamental ways to classify materials, distinguishing between pure substances and mixtures, noting that there are two different kinds of pure substances, elements and compounds. Then we are going to look at some of the different kinds of properties we can use to characterize, identify, and separate substances. Many properties rely on quantitative measurements involving both numbers and units. The units used in science are those of the metric system. Metric system is a decimal system of measurement. Now, when you do measurement, there are uncertainties inherent in all measured quantities, and these uncertainties are expressed by the number of significant figures you use to report the number. The number of significant figures is also used to express the uncertainties associated with calculations involving measured quantities. Lastly, we are going to talk about dimensional analysis. In dimensional analysis, you multiply, you divide your units just like you do with regular numbers, and in the end, you check to see whether the units is what you expected. So this is a very important way to check whether your calculation is correct or not. Chemistry is the study of the properties and behavior of matter. What is matter? Matter is anything that has mass and take up space. Property is any characteristic that allows one to recognize a particular type of matter and to distinguish it from other types of matter. Now, numerous experiments have shown that the tremendous variety of matter in our universe is due to the combinations of only 100 or so basic substances called elements. As you can see here, there are only 118 elements so far discovered. Chemistry gives you a background to understand the properties of matter in terms of atoms. We are going to see that the properties of matter have to do with both the kinds of atom it has, it's called the composition, and also the arrangement of those atoms. This is also known as the structure. Now, atoms can combine to form molecules. For example, in this figure, you see the molecular models of several different molecules: oxygen, water, carbon dioxide, ethanol, ethylene glycol. The white, black, and the red spheres represent atoms of hydrogen, carbon, and oxygen that combine to form the molecule. So notice how these molecules have very different compositions and structures. Now compare the molecules of ethanol and ethylene glycol. Notice how these two molecules have different compositions and structures. Even small differences in the composition or structure of molecules, like you see here, can cause huge differences in properties. Ethanol is the alcohol in beer and wine. Ethylene glycol is an automobile antifreeze. It basically keeps the fluid in your car from freezing at low temperature. The physical properties and the chemical properties of these two substances are very different in many ways. Their biological activities are also very different. You can drink ethanol and you will be happy, but you should never drink ethylene glycol because it's highly toxic. If you do that, you will end up like this guy. One of the challenges for chemists is to alter the composition and the structure of molecules in a way so that we can create new substances with new properties. Well, another reason why we study chemistry is we are surrounded by chemicals everywhere. You see them in your bathroom, in your kitchen, in your medicine cabinet, the computer you use, the car you drive, they are everywhere. And learning chemistry helps us to understand the material world around us and how it works. Here you see Clorox bleach, Pepto-Bismol. This is an antacid used for stomach problem, baking soda, as you see here. So when you interact with something, you can always ask, what are the compositions and the properties of this thing? How does it interact with us and our environment? How and why and when do they undergo change? And you ask these questions, whether it is a high-tech computer chip or a pigment used by a painter, or the DNA in a bacteria. There are two principal ways to classify matter. One is according to its physical state. Matter can be classified as a gas, liquid, or solid. Another way is classify matter according to its composition into element, compound, or mixture. Here you see the three physical states of water. Water vapor, liquid water, and solid water, ice. A gas, aka vapor, has no fixed volume, no fixed shape. It usually takes on the shape of the container, and you can expand it or you can compress it. A liquid has a fixed volume, but no fixed shape. It also takes on the shape of the container, and you can pour it. A solid has both fixed volume and fixed shape. You can understand these at the molecular level. In a gas, the molecules are far apart from each other and are moving at very high speed. Compressing a gas decreases the space between molecules. In a liquid, the molecules are packed very closely together, but still move rapidly, which allows the molecule to slide over each other, so liquid can pour very easily. Most of the stuff around us are not chemically pure. Pure substance is matter with distinct properties and composition that does not change from sample to sample. Pure substances are either elements or compounds. Elements cannot be decomposed into simpler substances and is composed of only one type of atom or element. So in this figure, A is an element, B is also an element. Compounds are composed of two or more different types of elements. So C are molecules of a compound, and this compound is made of two different kinds of atoms or elements. Mixtures are combinations of two or more pure substances. So here you see a mixture of elements and a compound. Currently, 118 elements are known, and I think about 92 of them are natural elements. They exist in nature, and then the rest are synthetic. They are man-made. So if you discover one, it will be named after you. This table listed the names of some common elements and their chemical symbols, which has one or two letters. The first letter is always in uppercase, and the name mostly came from the English name for the elements, as you see in the first two columns, or the name can come from a foreign name, as you see in the last column. The table in which the symbols for each element is put in a box. The box is called a periodic table. In a periodic table, elements are arranged in vertical columns so that related elements are grouped together. Most elements can interact with other elements to form compounds. For example, burning of hydrogen gas in oxygen produces water, and conversely, water can decompose into hydrogen and oxygen through a process called the electrolysis. The elements hydrogen and oxygen exist naturally as diatomic or two-atom molecules. In electrolysis, basically hydrogen is released at the negative electrode or the cathode, and oxygen is released at the positive electrode or anode. The interesting thing is that the amount of hydrogen molecules collected at the cathode is always twice the amount of oxygen collected at the anode. The same thing happens when hydrogen react with oxygen. As you see here, every two hydrogen molecules will react with one oxygen molecules to produce two water molecules. The observation that the elemental composition of a pure compound is always the same is known as the law of constant composition. Unlike pure substance, whose elemental composition doesn't change, a cup of coffee can have either a little sugar or lots of sugar. So coffee is a mixture. And the sugar and water are called components of that mixture. Some mixtures do not have a uniform composition properties and appearance. These are heterogeneous mixtures. For example, rocks. Mixtures that are uniform homogeneous mixtures. Air is an example. Also salt, sugar dissolve in water to form homogeneous mixtures. Homogeneous mixtures are also called solutions. Solutions can be solids, liquid, or gas. This figure summarizes the classification of matter, and you should be able to figure this out on your own. So we talked about the study of chemistry, we talked about the classification of matter. Now we are going to look at some of the different kinds of properties we can use to characterize, identify, and separate substances. Physical properties can be observed without changing the identity of substance. For example, color, density, melting point, boiling point, all these are physical properties. When you measure the density of a piece of wood or observe its color, you are not changing its identity. Chemical properties, on the other hand, describe the way a substance may change or react to form other substances. A common chemical property is flammability, how easily you can burn something. So when you measure the flammability of a piece of wood, a chemical reaction takes place called combustion reaction, in which the wood is turned into carbon dioxide and water. Some properties such as temperature, melting point, boiling point, density are called intensive properties. They do not depend on the amount of sample you use. Intensive properties are especially useful in chemistry because many of these properties can be used to identify substances. For example, if a liquid has a melting point of 0 Celsius, a boiling point of 100 degrees Celsius, and a density of 1 gram per cubic centimeter, you can be pretty sure it's water, regardless how much sample you use. Extensive properties depend on the amount of sample you use. For example, mass, volume. Changes can be classified as either physical or chemical. During a physical change, a substance changes its physical appearance, but not its composition. For example, all changes of state are physical changes. In a chemical change, aka chemical reaction, a substance is transformed into a chemically different substance. Here you see hydrogen burning in oxygen or in the air. And this is a chemical change because these two substances are transformed into a chemically different substance. In this picture, a copper penny is dissolved in nitric acid. And this is another example of a chemical change. Because each component of a mixture retains its own property, so we can separate a mixture into its components by taking advantage of the differences in their properties. For example, a heterogeneous mixture of iron and gold can be separated by cutter into iron and gold. A less tedious approach would be to use a magnet. We can also take advantage of the chemical difference between these two metals. Many acids dissolve iron but not gold. The two could then be separated by filtration. In filtration, a mixture of solid and a liquid is poured through, in this case, filter paper. It's very much like when you make coffee, you use a paper filter, and the liquid passes through the paper while leaving behind the solid. And in the case of gold and iron, the undissolved gold will be left behind. We have to use some other chemical reactions, which we will learn later, to recover the dissolved iron. Another method is distillation, which depends on the different abilities of substances to form gases. For example, if we boil a solution of salt, the water will evaporate and then condense and get collected in a receiving flask, leaving behind the salt. Different substances stick to a surface, such as paper, differently, and they also dissolve in the same solution differently. These differences can also be used to separate mixtures, and this is the basis of chromatography. Literally, it means the writing of colors. Here, you put a droplet of ink spot on a piece of paper, and then you dip that paper in the water. Water begins to move up the paper. Water move past the ink spot, dissolving different components of the ink at different rate, and now the ink has separated into several different components. Yes, the guidelines for doing science are known as the scientific method. We usually begin our study by collecting data. It's called the observation or experiments. As we perform our experiments, we may begin to see patterns that lead us to a tentative explanation or hypothesis. Eventually, we may be able to summarize all the observations in a single statement or equation called a scientific law. If a hypothesis is sufficiently general and is continually effective in predicting facts yet to be observed, it is called a theory. The units used for scientific measurements are those of the metric system, which was first developed in France during the 18th century. Because traditionally the US has used the English system, so even though the metric system has become more common, the US still uses the English system today, as you see on many food products. English system, and this is the metric system. In 1960, an international agreement was reached specifying a particular choice of metric units for use in scientific measurements. These preferred units are called SI units. As you see in this table, this system has 7 base units from which all other units are derived. Prefixes are used to indicate decimal fractions or multiples of various units. This table shows the prefixes commonly used in chemistry. Now for length, the basic SI unit is meter. A mass is a measure of the amount of material in an object. Its SI unit is kilogram. The SI unit for temperature is Kelvin. Both the Kelvin and the Celsius are used in science. In the US, Fahrenheit is used as the temperature unit. And this is how you can convert from Celsius to Kelvin and from Fahrenheit to Celsius, or vice versa. Figure 1.19 shows how volume unit is derived from a length unit. So the volume of a cube that is 1 centimeter on each side is 1 cubic centimeter. Another example of derived unit is density. The unit for density is a gram per cubic centimeter, or gram per mil, and these are derived from the unit for mass and volume. Precision is how closely individual measurements agree with one another. Accuracy is how closely individual measurements agree with the true value. This is a good accuracy and good precision. This is poor accuracy, but good precision. Here you see poor accuracy and bad precision. In the lab, we often perform several trials of the same experiments, and then we average the results. The precision of the measurements is expressed in terms of the standard deviation, which reflects how much the individual measurements differ from the average. Now let's say that you weigh a butterfly on an analytical balance capable of measuring to the nearest 0.0001 gram. You would notice that the reading fluctuates. It reads 0.2735 gram, but sometimes it can read 0.2734, and sometimes 0.2736 gram. So we usually report the weight or the mass as 0.2735 plus minus 0.0001 gram. Drop the plus minus because we know that there is always some uncertainty in the last digit of the measured quantity. So measured quantities are usually reported in such a way that only the last digit is uncertain. This is a cartoon showing two guys in a lab that has an atomic clock. My goodness, it's 12 o'clock, 15 minutes, 0936420175 seconds, time for lunch. All digits of a measured quantity, including the uncertain one, are called significant figures. The greater the number of significant figures, the greater is the certainty implied for the measurement. Now, when you see the result of a measurement, how do you know? How can you determine the number of significant figures in that measurement? Here are some basic rules. In any properly reported measurement, all non-zero digits are significant. Zeros may or may not be significant, depending on how they appear in the number. Zeros between non-zero digits are always significant. So, for example, if the measured mass is 1005 kilogram, then this result has 4 significant figures. Zeros at the beginning of a number are never significant. So if you get 0.02 gram, then the result has only 1 significant figure. Zeros at the end of a number are significant if the number has a decimal point. So if the result shows 0.0200 gram, and that means the measurement has 3 significant figures. Now it can be tricky when a number ends with zeros but has no decimal point. It is normally assumed that the zeros are not significant. Exponential notation can be used to clearly indicate whether zeros at the end are significant or not. For example, a mass of 10,300 gram can be written in exponential notation, showing either 3 or 4 or 5 significant figures depending on how the measurement is obtained. So, for example, here you can write 10,300 gram in exponential notation as 1.03 times 10 to the 4th gram. If you write it in this way, then there are 3 significant figures, 1, 2, and 3. And if you express the same result in exponential notation as 1.0300 times 10 to the 4th gram, and that means the result has 5 significant figures. As we mentioned earlier, the greater the number of significant figures, and the greater is the certainty implied for the measurement. Now, how do you determine the number of significant figures in a calculation? Well, here are some of the rules. The least certain measurement limits the certainty of the calculated quantity in the final answer. So for addition and subtraction, the result has the same number of decimal places as the measurement with the fewest decimal places. Say here when you are adding three numbers, so you add them up and you get the sum 104.842 in this case, and then you see which number has the fewest decimal place. Well, in this case 83.1, it has only one decimal place, so your final result should also round off to one decimal place, which give you 104.8. For multiplication and division, the result contains the same number of significant figures as the measurement with the fewest significant figures. So here is an example. You are measuring the area of a rectangle. So one side is 6.221 centimeter, another side is 5.2 centimeter. So you multiply these two numbers to get the area. So the product of these two numbers is 32.3492 square centimeter. Then you see which measurement has the fewest significant figures. Well, this measurement has 4 significant figures, and this measurement has 2 significant figures. So your result should also have 2 significant figures, and you round off your result to 32 square centimeter. So for addition and subtraction, decimal places are counted, and for multiplication and division, significant numbers are counted. Exact numbers can be treated as if they have an infinite number of significant figures. Now, there are some rules in rounding off numbers. When you round off a number, look at the leftmost digits to be removed. And if it's less than 5, don't change the preceding number. For example, if you're trying to round off 7.238 to 2 significant figures, so 38 are the 2 digits you are going to remove, and 3 is the leftmost digits to be removed. And you want to see, and then you check to see whether it is less than 5 or not. If it's less than 5, then you don't change the preceding number, so the result is 7.2. If it's equal to or greater than 5, then you increase the preceding number by 1. For example, you are trying to round off 4.25 to 2 significant figures. You should write your result as 4.3. In dimensional analysis, we keep all the units throughout the calculations. Units are multiplied, divided, or cancelled, just like you do with regular numbers. This helps to ensure that the solutions to the problems give the proper units.